Welcome once again to the course Applied Econometrics, and as you know, we are discussing dynamic panel data model. So in our last class, what we were discussing was about how instrumental variable approach can be applied to estimate a dynamic panel data model, wherein neither first difference nor the fixed effect transformation was really helpful. So this instrumental variable approach was basically based on the Anderson and Hesios suggestion. Firstly, they only suggested that we can take the first difference of the original dynamic panel equation, and since the difference one of the explanatory variable after taking the first difference is getting correlated with the error term, what we can do, we can still use the first difference model, but we can use an instrument for that explanatory variable which becomes endogenous after first differencing, right? So before we talk about today's Arellano-Bones method of generalized method of movement, so my intention is to give you a brief idea about what exactly is generalized method of moment so that you can better understand Arellano-Bones approach. So I would like to quickly recap what we have already discussed in our previous class. So it was all about discussing different types of instrument metrics under three approaches. Firstly, we started with Anderson and Hesiod, then we discussed about Holziakin et al, and lastly we saw how Arellano and Bond basically modified the Holziakin et al.'s idea, right? Just quick recap of the model. So our dynamic panel equation was this. So dynamic panel data model, once again, dynamic panel data model. So our equation was yi t equals to a rho yi t minus 1 plus, let's say, beta xit plus ai plus vit, and this ai plus vit is actually the combined error term, which is uit, and then we took the first difference yi t minus yi t minus 1 equals to rho yi t minus 1 plus yi t minus 2 plus beta xit minus xi t minus 1 plus vit minus vi t minus 1, and since this yit minus 1 is actually correlated with vit minus 1, so this particular explanatory variable is correlated with the transformed error term. So that is why we say that we need to use IV for this particular variable yit minus 1 minus yit minus 2, which is basically, this is nothing but, we can say that this is delta yit minus 1. And what are the instruments we said? We said either we can use the twice lagged of the level yit, that means it will become yit minus 2, or twice lag of the difference, that means delta yit minus 2. So initially we were discussing about yit minus 2, taking that as an instrument, and then in Anderson and Hesios approach, in short, Anderson and Hesios approach. So the instrument matrix was this. So first observation would be lost, and then we'll get yi1 and then yi2, and then it will become yi t minus 2, t minus 2, that is your instrument matrix, right? So this is, that means yi1, this is for the second period, t equals to 2, and then this is equals to t equals to 3. First observation is available for t equals to 3, and then second observation, first row indicates t equals to 2, and that observation is lost for each panel, so sample size goes down. And if we take the thrice lag also as an additional instrument, then your Z matrix become basically, this is yi1, yi2, then yi t minus 2, and when I take the thrice lag also as an additional instrument, I will lose 2 observations. This will become your instrument matrix. So that means if I, in Anderson and Hesius approach, when I add more lag into the instrument matrix, my lag length is increasing, but at the same time my sample length is decreasing, and that is why we said that there is a trade-off between lag length and sample length. That was Anderson and Hesius approach. And then to overcome the sample length, what Holjakin et al., they basically suggested that instead of taking too many lags as instrument, we will take only one instrument for each period, and that is second lag of the level variable, and we will replace all the missing observations as 0. So in Holjakin et al., Holjakin et al., they said that instrument matrix should be this way. So I will take only second lag as instrument, and all the variable I will replace as 0, and all the missing observation will be replaced as 0, and this will become yit minus 2. So that means in each period you can see that I have only one instrument per period. This is t equals to 2, this is t equals to 3, this is t equals to 4, and this is t equals to capital T. So this is Holjakin et al.'s approach, one instrument for each period and replacing all the missing observations as 0. And then we also discussed that even though setting 0 as in the place of missing observations appears like arbitrary, interestingly each column of this instrument matrix, they satisfy the orthogonality condition. That means expectation yi t minus 2, yit minus 2, and your differenced error term vi star is actually 0. So vi star is vit minus 1, and then in this approach, even though we ensured enough sample, our lag length was confined only to 2. And based on this Holjakin et al. Approach, lastly we discussed about Arellano and Bond's instrument matrix, wherein Arellano and Bond says that instead of using only one instrument for each period, why don't you do one thing? You take this instrument, you take the idea of Holjakin et al., that means second lag of the untransformed variable for each period, and also additionally whatever lag is available for that particular period for all the variables we will include. And then we said that for endogenous variable, it would be lag 2 and higher for predetermined variable, which includes uh, uh, your endogenous variable as well as lagged dependent variable. We will take even first lag also, because that would be correlated only the error term with t minus 2 and earlier. So then we said that in Arellano-Bonds approach, our instrument matrix was this. Right. So this is yi1, yi1, and then this is yi2 and yi1, and then 0, 0, 0, yi3, yi2, yi1, and then this is basically your Z matrix in Arellano and Bonds method. That means we can easily see that in Arellano and Bonds method, we have too many instruments. So one instrument for second period, two instrument for third, three instrument for the fourth, and so on. So too many instruments are used in this method, and then this method is basically dependent on, we say that Arellano-Bonds method is basically a method of generalized method of moment. Why we are using moment? Because we are using all potential orthogonality conditions available. That means we are using all potential moment conditions here, and that is why it is an approach called generalized method of moment, wherein I will tell you what exactly is method of moment, where your number of instruments are actually much more than number of parameters to be estimated. So that means this is a case of over identification, right? Over identification. And then we also said before we go back to the generalized method of moment, I would like to again remind you what are the major assumptions that define the context of Arellano and Bonds model to be applied. We need to keep this thing in mind. So we have only one left hand side variable which is dynamic in nature. So that means if I go back, you can see that only left hand side variable which is dynamic in nature, yit minus 1. And this yit minus 1, the addition of this lagged variable makes the system dynamic. And if you recall, we have also discussed that for dynamic stability, the value of rho should be less than 1. Okay. So if rho equals to 1, then we proved in our last class, then the model does not become dynamic, it becomes a static one. And if rho greater than 1, that does not define the stability of the dynamic system. You can easily understand by subtracting yit minus 1 from both the sides. So this would become yit minus 1 equals to 1 minus rho into yit minus 1 plus beta xit plus ai plus vit. From that equation, you can easily understand that to get a dynamic panel data model and dynamic stability, rho should be less than 1, and that is the reason we say this is also partial adjustment model, because rho equals to 1 means complete adjustment in the same period. That does not give any dynamic panel in nature. Okay. So with this, now what I will do, I will just remind you the context. So number one, there is only one variable in the left hand side which is dynamic in nature, and then the relationship, second assumption, the relationship is linear. Okay, this is a linear relationship between yit with yit minus 1 and any additional explanatory variable that might be there in the system. Number 2, and very importantly, here as we said that number of time period t should be small compared to number of observations in. So, it is a case of micro panel where t is very small and n is very large. Why this is so? Because when you take the first difference, we said that first difference estimate would be biased and inconsistent, and the order of bias will be 1 by t. So, that means as time period increases, bias will go down. So, that means if your t is very large, then actually we do not have to use any other dynamic panel data model to estimate. We do not need any separate technique to estimate this type of dynamic panel data model, simple OLS we will do. But when t is small, then we prove that the bias is quite high, and even when t equals to 30, we prove that the bias is 20% of the original estimates. That is the second assumption. And then we say that we have one unobserved individual specific unobserved effect in the right hand side, and then we have also mentioned that we have autocorrelation of order 1 in the system, because that is by the construction of the model says the moment you introduce lag dependent variable, it will result in autocorrelation. So, AR1 should be there in the system, but not AR2, and we should not be happy if even AR1 is also not there, because the moment AR1 is not there, then you should understand that means this model is not at all dynamic in nature. Okay, that was the situation. And then we said that autocorrelation and heteroscedasticity will be there within each of this individual, but not across. Within each of the individual, but not across. So, these are the contexts, these are the assumptions that define Arellano-Bones context for dynamic panel data model, right. Then now, after discussing this context, I will do what I will do in today's class, that in today's class I will be discussing mainly the method of moment. I would like to give a brief overview of method of moment. So, this is basically GMM. I am going to discuss about GMM, or generalized method of moments, or in short GMM. Now, before we go and discuss about GMM, let us see once again go back to our ordinary least square method, and we will show that OLS also as a method of moment estimator, right. OLS estimator what we got, that we can derive from the method of moments approach also. So, let us assume for the time being, this is our model yi equals to xi beta plus ui, okay, and here I equals to 1. Why I am writing xi beta instead of beta xi? Because these are all matrix notation. That is why yi equals to xi beta plus ui, that is my matrix notation. And then, if you recall, one of our standard assumptions in classical linear regression model, that none of my explanatory variable should be correlated with the error term. Okay, none of my explanatory variables should be correlated with my error term, And in terms of expectation, what you can write, that means OLS assumes no correlation between explanatory variables and the error term. This is the assumption, okay? And if this assumption is violated, then we say that OLS estimates will no longer be consistent. So, basically this means expectation of xi and ui equals to 0. Okay, no correlation between explanatory variable and the error term indicates expectation xi ui equals to 0. This is called a population moment condition also. Writing this expectation xi ui equals to 0 is a population moment condition, and then this actually implies expectation of xi prime instead of ui. Now I will replace, what is ui? Ui is nothing but yi minus xi beta. So this will become yi transpose minus xi transpose into beta, that is equals to 0. Okay, very simple. In place of ui I am just putting yi prime minus xi prime beta. This is all transpose basically. Okay, now the method of moment condition, the method of moment estimator, the method of moment estimators basically solves estimator solves the sample moment counterpart of this population moment condition. Okay, that is why I am saying the method of moment estimator solves the sample moment condition. And what is the sample moment condition? Basically, it is 1 by n, where n is the sample size, 1 by n summation. You take the summation of this xi prime and then yi prime minus xi prime into beta hat, right? In this is equals to 0. Okay, this is equals to 0. I have just taken the sample moment counterpart of this population moment condition, which is 1 by n summation xi prime beta xi prime yi minus xi beta. And if you solve this equation, then you will get your OLS estimator as beta hat, which is nothing but x prime x inverse x prime y, okay, which is the OLS estimator. So that means what I have proved, that OLS estimator is nothing but a sample moment condition derived from the population moment, derived from the important assumption that no explanatory variable should be correlated with the error term, which basically gives a moment condition, which is population moment condition and expectation xi ui equals to 0. So from that equation I have derived the sample moment condition, and after solving that sample moment condition I got my OLS estimator as the moment estimator, method of moment estimator also. Now I will come to instrumental variable estimates, instrumental variable estimation, instrumental variable estimation. So, what I will do in this instrumental variable estimation, basically the assumption what was there in OLS that no explanatory variable should be correlated with the error term. Now I assume that some of the xi's, some of the explanatory variable are actually correlated with the error term. That is the assumption, as we will know, because that will lead to endogeneity condition, and endogeneity means we need to apply instrumental variable approach. We need to find out an instrument, let's say Z, which will be highly correlated with the endogenous variable but not at all correlated with the error term. So that means let us assume some of the explanatory variables or xi's are actually correlated with the error term. So if that is the case, then what happens when error terms are correlated with explanatory variable? OLS is inconsistent. So OLS is inconsistent. And what does inconsistency mean? Once again, if I recall, inconsistency means the condition beta hat beta, the difference between beta hat minus beta should be very minimum, less than the minimum quantity delta, and probability of getting such beta when n tends to infinity, that is equals to 1 minus epsilon. This is called consistent. This is consistency condition. So that means as n tends to infinity in a large sample, my beta hat will converge to beta. So that means the difference between beta hat and the true population parameter will be very small, and probability of getting such beta is also almost 1, because epsilon is also very small quantity. So this is called consistency. This is consistency property of OLS. And this consistency property will no longer be valid the moment we assume that some of the explanatory variables are actually correlated with the error term. So if that is the case, OLS becomes inconsistent, and we need to identify instruments that are highly correlated with the endogenous variable but not at all correlated with the error term. Okay, with the error term.